Okay, so we're recording now, and what we've talked about so far was models for the laser, and so the four-level laser model, and all that's good. Like I said, laser engineers uh, work with these equations for three-level and four-level lasers, and that's all they know from the point of view of the theory, and it's sufficient. Um, Now we have only looked at near threshold, so that's one thing that we would like to do, look a bit above threshold also. And it turns out that it's a simple modification, so we will discuss that as well. But first, I thought that, in terms of what you can take away from the course, I thought that a good thing to do, so these are the final two topics that we would like to talk about. And a good thing to do would be discuss light matter interaction in some general terms, so that because that's a broad topic, it's something that you will likely encounter in some form. And so then it's got some E&M principles in it, and some more widely applicable concepts that I expect will come in handy for you. Okay, so the two topics that I need to talk about right now, and today is uh, the 23rd. The two topics that I'd like to talk about are um, the first thing. Let me just, okay, so the first topic is a microscopic theory of light matter interaction. And why is this important? Because first of all, there were several things mentioned in our syllabus about why is the sky blue, and um, why are, I guess, clouds are white. We've discussed that a little bit, but we haven't said why. Like where does that high frequency dependence of Rayleigh scattering come from? Why is blue scattered more than red? We haven't really discussed that. So why is the sky blue, and why is the sunset pink? And there's absolutely no way I can show you the demo right now. And there was a demo for that too, but I just don't know if there's any way to do that. Um, and why are metals always shiny? These kinds of things. There is something very important lurking in there, which has to do with the metals shiny, at least. There's a very general useful principle that if there is a material that is a good absorber at some frequency omega, let's say. So if you have a material that's a very good absorber at a certain frequency omega, then it is also a good reflector at that same frequency omega. That's a counterintuitive kind of statement, but it's a intriguing and interesting law of nature. Comes right out from Maxwell's equations, actually. That if you can make a material that is a good absorber, now note that the absorbing is a property of the bulk, right? So the bulk material is what absorbs, whereas reflection happens right at the surface, right? And so, I mean, what happens at the surface, what happens inside the bulk, there's this interesting relationship between them. And it comes right out of Maxwell's equations, and that is the answer why all metals are shiny. Okay, because um, um, well, will let's see if we how we get to that topic. But these are broad topics of topics of broad importance, and so they come up quite a bit, and it all depends upon this microscopic theory of light matter interaction, meaning uh, more specifically that we will go after the refractive index. Now, the refractive index is something that you only know kind of macroscopically, speed of light, in vacuum divided by the speed of light in the medium. And but uh, it's we don't really have a microscopic theory for it, and so I mean, we do, but we haven't discussed this in class. So I think that's something that would be useful. And then the other thing that would be useful is um, you know contributions to line width, to spectral line width. How about that? Okay, and so in here you have examples such as, well, first of all, there's the natural line width, and that's something that we've discussed. We've mentioned the word at least, and that arises from the Heisenberg uncertainty principle. But then there is also, Doppler line width. Okay, and this is because atoms are moving; they're not stationary, and so there's a certain, by line width, spectral line width. What I mean is that we've already discussed how to make a laser single mode, right? And so there you go, it's single mode. But there's always this line width, right? And so what contributes to the width there? Why is it not perfectly monochromatic? And so it's not perfectly monochromatic because of these contributions, okay? And then you have, then there's also something called power broadened, meaning just because the laser is putting out light, there is a power broadened line width. And this happens due to saturation effects. The thing to remember is that the laser line width ends up being smaller than all of these. So laser line width is much smaller. Okay, so and I'm not sure how much time we will have to discuss why it is so much smaller, but these line widths are important. Important. The physics is important, and you would have measured each one of those in the lab. So that's where I'm waiting for the video to show me, to guide me on how much I want to say about these. You would have measured each one of these line widths in the lab. And the laser line width is much, much smaller. I guess one quick answer is because it relies upon stimulated emission. Okay, so, and stimulated emission, the line width for stimulated emission is much narrower. Now those words are very cryptic, and I can't say too much more about it right now, but we'll see what we can say about this thing. But anyway, let me get started with the microscopic theory of light matter interaction, and let me first remind you about the stuff from E&M that you've learned already. Okay, so so before starting on the microscopic theory, for the refractive index or light matter interaction. I'm using the two words interchangeably, the two phrases. So before starting on microscopic theory for the refractive index, let's remind ourselves of basic ENM, okay, which you've learned. And what that relates to is the fact that what you have learned is that if you have some material, I mean, I'm just reminding you of electric polarization because that's where, basically what I'm reminding you of is Maxwell's equations in materials. Okay, and so what you have learned there is this electric polarization. Okay, and so what you've learned is that if you place some material, and we've been calling them dielectric materials and things, if you place them, some material between a capacitor, let's say, it's back to boring old electrostatics. But the reason is that, okay, so there's an electric field from the charges on the capacitor plates. And this electric field, I mean, so it's just like if you had an electromagnetic wave coming into material, then as you know, we only look at the electric field component, right? The magnetic field component, I think we've talked about that. Have we talked about that? The magnetic field component never, it does not have as strong an interaction, okay? I believe we have discussed that. I sometimes get confused because I talk about things with so many groups of students. But I seem to recall that we did talk, we said that the Lorentz force, uh, I seem to remember us saying that why do you only talk about the electric field? Right? Guys, do you remember, everyone? I seem to remember us discussing this, that, why do you only talk about, like when we look at the polarization and stuff, then we only look at the electric field, and we never discuss what's going on with the magnetic field. And I feel like at some point we had discussed why that is the case. Did we not? Do you recall? Does anyone recall?
I have no recollection of this.
I missed the question, but I also probably don't.
Okay, so we've never discussed why is it that, when we were doing when we were doing the polarization, the polarizers and the wave plates and things, why is it that we only talk about the electric field and never the magnetic field? I seem to think that maybe I might have said something on the whiteboard, but not really written anything down. I think that's what happened. Well, if that's the case, then I think we have to talk about it now. You might have wondered about this, that whenever we talk about light interacting with matter, as you can see from wave plates and polarizers and other things, that you only worry about the electric field in the electromagnetic wave. You never discuss the magnetic field, very rarely, unless you are dealing with explicitly magnetic materials or looking for explicitly magnetic effects. The first order interaction between light and matter is always about the electric field, okay? And so why is that? And there's a very simple reason. I'll just say this, that aside in light matter and it's much deeper. It goes much deeper than this too. Like, I mean, in the research, whenever we talk about light and atoms and stuff, it's always the electric field. So in light matter interaction, we almost always only worry about how the electric field of the electromagnetic wave, the EM wave, interacts with the material, not the B field. Why? And the answer has to do with the Lorentz force. Okay, so the Lorentz force is, that's, if you have a charge Q, and let's say it's moving with some velocity V, and there is a electric field in the vicinity, okay, something like that, and let's say there's also a magnetic field in the vicinity, like that, then we know that the force on this moving charge is given by the Lorentz force, right? And this is what the Lorentz force looks like in SI units. In the 600 level course and in advanced QED and all, often we don't use SI units, we use something called Gaussian units. And the reason is that in SI units, you always have those horrible like epsilon naughts and mu naughts, and C never shows up in any of the equations in SI units. There's no C, no speed of light, even though the electromagnetic wave is light. And so the connection with light is hard to see. In Gaussian units, everything is expressed in, C shows up in the equations. I mean, one of the bad things about SI units right here is that from relativity that electric field and magnetic field are two identical aspects of the electromagnetic wave, meaning half the energy is in the electric part, half the energy is in the magnetic part. From relativity, you know that something that appears as an electric field to one person may appear as a magnetic field to the other. Like if you have an observer traveling at relativistic speeds perpendicular to some light wave that is moving along, they may see it all as a magnetic field. And so I'm not necessarily saying the exact correct thing here, but depending on how the observer is moving, they may see a completely electric field or a completely magnetic field, all right? So there is no difference between the electric and the magnetic fields in a certain sense. There are two different vibrations of the same wave, okay? And so it is disconcerting that your units, the SI units, make them look like they're something different. Their dimensions are different. Electric field and magnetic field have different dimensions, right? Because the units, right? The B is multiplied by velocity. And so velocity times B is the same units as E. They look like they're two different things. This is very counterintuitive. I mean, it's not reflecting reality. In the Gaussian unit system, this is taken care of much more elegantly. The Gaussian units, Lorentz force is Q E plus the velocity, right? So this is velocity divided by C cross B in Gaussian units. And so now you see that the electric field, the magnetic field have the same units, okay? And C appears in the equation. And this right away tells you why in light matter interaction this part is negligible. Why? Because if you think about what matter is, essentially matter is a nucleus and there is an electron going around. Okay. And for some reason, I remember me talking about this in class, but maybe I didn't write anything down. I certainly couldn't find anything quickly. So here's your negative electron, right? And you can calculate the speed of this electron going around the nucleus, because if you recall from some place somewhere, you must have heard that the ionization energy for the hydrogen atom. Okay, so ionization. I mean, I'm doing this because I want to find out what the velocity is for this electron as it goes around, and it turns out that there's so 1/2 mv squared is less than a certain amount, because the ionization energy for hydrogen atom is 13.6 electron volts. You may have seen this in some connection. Well, that means that if 13.6 electron volts is supplied to this electron, it's going to have so much energy that it's going to go around so fast that the nucleus cannot keep it bound and it's just going to leave. So if you want to strip the atom of its electron, if you can supply it with that much energy, it will leave the atom. So that means the kinetic energy is certainly less than 13.6 electron volts. And so if you plonk in the mass of the electron, so that's one reason why I'm talking about all these issues, because these are things that, irrespective of how much you got about lasers, these are so basic and so sort of all-affecting concepts that, you can walk away with these, and I think that, and these are things that normally are not talked about in textbooks and, standard forms of E&M and stuff. So I feel like they might be useful. So anyway, this times the V squared is less than 13.6, and electron volt, if you recall, is 1.6 times 10 to the minus 19 joules. So these are all SI units, and you can solve for V, and the V turns out that it's less than 0.00, and I forget if it's I think it's 0.007 C. So it's fast. It's fast, but it's not really relativistic, meaning that this guy here is pretty small. And so that's why you can neglect this contribution, because the electric and the magnetic parts of the electromagnetic wave are about the same in size, okay? But it's this factor that, because of the electron motion around the nucleus being non-relativistic, it's fast, but it's non-relativistic. And that's why in our course, for example, we only were looking at what happens to the electric field. We had polarizers and wave plates, and we only talked about the electric field. Okay, because it's in the end it's the electric field that interacts, that has a stronger interaction with materials. Okay, unless you have ferromagnetism going on or other things, and unless there's some collective magnetic effect. Okay, so does this make sense? Yeah. So yeah, I mean, I don't know. I don't see nobody's head is visible to me, and understandably, people are muted, so I don't have any idea if people are with me or...
You're doing great.
What's that?
We're doing good.
Okay, good. So let me just put that down there. So that's why I'm reminding you of the electric field interaction, and you've done this in basic E&M, okay? we studied the concept of polarization, and what happened here was that the positive charges dragged some negative charges over to the left and repelled, or rather these guys, attracted some of the so you polarize the medium, right? And um, let's see. So and what happens then is that you induce a dipole, right? Because now you have mostly negative on this side, positive on the other. So you've induced a dipole. You've polarized the medium and you've created a dipole, and this induced dipole points from the negative to the positive, right? Always, like the dipole moment is always. So let me just say, uh, electric polarization. Let's call it, big P, and this is of course proportional to the electric field, right? And um, if I look at, um, let me try and connect it with the, with what's going on with the atoms here. So inside this material, what really is happening is that, um, you know, uh, so inside this material, let me just draw, like this is the atoms. I think three are enough to show what's going on. And so they're the simplest microscopic picture. And you've had this in your freshman and sophomore physics. And so now there's an electric field like this, right? This electric field. And so what it does is it takes the negative electron cloud and sort of jerks it over to this side, right? Like that. And so you see that now for the left column of atoms, you can see that this side is more negative. That's where the electron cloud is mostly, right? So you have negative on this side. And for the rightmost column, the negative electron cloud has been displaced over to the left. And so the more positive part, so the atom is polarized, right? Every atom is polarized. And, um, and so the induced dipole moment points in this direction. Inside the medium, it all kind of cancels out. But because of the stuff on the left and right extremities, there's an induced dipole moment. And uh, I guess let me first, for one atom, um, we define something called a lowercase p, okay? And this lowercase p is, of course, proportional. And so this is the induced dipole moment per atom, right? It's in one atom. And this is equal to, it's proportional to the electric field. And we introduce a constant called alpha. I'm sorry that there are many alphas floating around. I think we had one for the absorption coefficient and all that, but this alpha is called the polarizability. The polarizability of the atom. Okay. Um, and as you can see from this, the polarizability alpha. Alpha equals polarizability, and it's defined as, just reading off this equation, it's the induced dipole moment per atom per unit electric field. Okay, so that's your polarizability. And the if I take the polarizability, or rather, if I take the induced dipole moment per atom, so the induced dipole moment, this is the induced dipole moment per atom, and if I multiply this by the number density of atoms, okay, so this is number density of atoms. So what will I get? So it's the induced dipole moment per atom multiplied by the number density of atoms. Well, what I get then is the induced dipole moment per unit volume, right? Because this is per atom, and then I'm multiplying it by the atoms per unit volume. So this is the induced dipole moment per unit volume. And the reason I brought this up is that this guy is actually equal to this electric polarization, the P field here. So this thing here is the number density times the induced dipole moment per atom. Okay. So, and this is all proportional. This is not alpha. Oh, I really need to. Oh man. So not only is there alpha, there's also proportional signs all over the place. But this is a proportional sign. This was alpha. I don't know how to. I mean, this is what is used in textbooks everywhere. So, okay. So this is something we've studied before. Now, I want to get rid of this horrible proportional sign here. So I will remind you that the electric polarization is also written as, okay? So this thing here, the P, this polarization, and this will remind you more of things that you've seen before. The electric polarization is written as, so it's proportional to the electric field, and the constants of proportionality are, there is a epsilon naught multiplied by a susceptibility. Okay, so this is the relation that you've seen before. So let me just write out what these things are. So the electric polarization is epsilon naught susceptibility electric field. Now let me just write out what these terms are. So this is the dielectric permittivity of vacuum. This guy, the chi sub E, is the electric susceptibility of the medium. Okay, and E is the electric field. So this is this right here is referred to as the macroscopic picture, okay, for light matter interaction. As long as the when you studied Maxwell's equations, then you were also told that this is the hallmark of a linear medium. Okay, meaning polarization is linearly proportional to electric fields. So this is a linear medium. You also have nonlinear media where the polarization can go as E squared, electric field squared or cube and so on. And there is a whole industry based on nonlinear materials. but 99% of things that we see is all linear stuff. And so this is the macroscopic, this is a macroscopic linear medium. Macroscopic linear response. Okay. All right. So that's basically what you've seen before. Okay. And now we are tasked with, coming up with a microscopic theory. Let me, I guess, let me just say one more thing here and then wrap this segment up here. So one thing that we can see from this equation is that the polarization is the number density of atoms times the atomic dipole moment, the dipole moment per atom, right? And this is equal to epsilon naught times the susceptibility. This is the electric susceptibility in there, okay? From here, we also, this guy here is also n, and the little p was alpha times E, right? So alpha times E, where this is the polarizability. So just by looking at these two now, you can infer that the susceptibility is n times polarizability divided by epsilon naught. And so this is something that we will use up ahead. Okay, and all right, so this is how you talk about a medium interacting with an electric field. All right. Let's see. There's something else that you need to remember from macroscopic stuff that you've done before. Let's see. So one thing we also want to recall Maxwell's equations in a material. Okay. So that's something that we will have to remind ourselves of. And basically what we'll do is that, we wish to derive the wave equation for the E field in the medium. Okay, and why do we want to do that? Because basically to get to the refractive index. Because in vacuum, your wave equation looks like, in vacuum, the wave equation looks like, there's the spatial part, and then there you go. But in the medium, And we just want to re-examine where that comes from. In the medium, instead of a C like that, what you get is minus, and there's a refractive index. Okay, and so we just want to remind ourselves where this comes from. And so then that would conclude our macroscopic theory for the refractive index. Okay. Um, yeah, we talked about atoms a little bit, but this was a very naive sort of freshman view, and we only introduced this, the polarizability for the induced dipole moment per atom. But it's so we introduced the concept, but we didn't really need to know too much about what the atom looks like or what it does in order to uh, write anything that we've done here so far. Um, but from this macroscopic picture, we will be able to write down some, what is our knowledge about the refractive index that we can write down from here. And so we'll do that first, and then we will come up with a microscopic theory for the refractive index. Okay, so I've been talking for 40 minutes. I think that I would like to give everyone a 5-minute break here, and then we will resume from there. And so let me stop the recording.